Okay, so who is asking for recording the session? You can go to this link on YouTube and you can watch this session anytime. Okay. Okay, so let's start the session now. Am I audible? Just somebody can confirm quickly.
Yes, sir.
Sir,
Yes,
you're
yes, sir.
audible.
Okay, okay. Okay, so in that session, I think ma'am has already discussed until because it is written there, so this part is discussed. Arun Kumar, from the next time, please join from your official email ID so that I don't have to admit you into the meet, okay? Because only official members are allowed. Okay. So in this session, this part is already discussed. This is also. I'll start where the ma'am has left. Okay.
One thing, sir, in GeoGebra R3, how to see it? Can you?
GeoGebra R3.
Yeah.
R3 is just 3D, right?
Yeah.
So
Yes, sir. Actually, I have tried to see, but I am not understand. Means
uh, how, I mean, what to understand? Because you are
means
saying just
what the figure tells us about what we are seeing in a three dimension. Like
there is a plane. Okay, so
yeah.
uh, suppose uh, okay, why it is not showing? Okay, so this is line,
Yes, sir.
and if we put two variable, so this is clearly in 2D, right? If we
Yes.
put two variable here,
Yeah.
x and y, and suppose okay, so it is not working. I don't know. So this is I can show you in this slide as well. Itself.
Okay.
This is R3. Mm, okay. This slide somewhere actually there is a picture. Okay, 1 minute.
It was in the beginning, sir.
Oh,
Yes, sir.
this is 2D. Okay.
Yeah. Yes.
R3 there is a Z axis. That's it.
Yeah. Yeah.
Nothing to. Yeah, this one. This is
This
R3.
is yeah. But what's what tells this figure? What we can understand from this figure? Only just
Yeah, so as you can see this shaded portion, this is a plane, right?
yeah.
So this blue line, this is z-axis, this is height, you can see. So this is plane and this is blue axis is height. So height term is also added here. So this is okay. And rest of the things you will see as you go in the course, okay? Then you understand what is why we use this, okay?
Okay.
So basically, you can say just a point like 1 comma 2. So
Yeah.
this point is in 2D plane, right?
Right.
But 1 comma 2 comma 3, this is in 3D. So so 1
Correct.
comma 2 can be represented somewhere in this plane. This is shaded plane, okay?
Yes.
But 1 comma 2 comma 3 will be some point like this.
In jet axis.
Yeah, this black vector you can see, black line. This is okay, and this green one is in the plane. Okay, so this is in 2D and this is in 3D, which
Right.
is our side. Okay. Okay, so this part is already discussed. Uh, what is I think this multiplication of two matrices. Okay,
Yes.
from here I'm taking. So these are the some conditions for the
So this
matrix.
is also discussed actually. She discussed in a different PDF. She didn't annotate it here.
Yeah, this one. Right.
Sir, the last topic she discussed was properties of determinants.
Yes, sir.
Determinant. Yes, sir.
Yes, sir.
Uh, this one, right? I guess linear equations are already discussed. This part is discussed or not?
Done, sir.
Okay, this is also discussed. What is the no solution and infinite solution? This part is also discussed, right?
Yes, sir.
Yes, sir.
Yes, sir.
So you can begin with
Yeah,
determinants.
yeah. This,
Atul, I guess you have to start from page 15, determinant of A transpose.
okay, 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 understood.
Sir,
Hmm.
sir, my problem is a system of linear equation. In in the finding of matlab, whether
Yeah, you
the
can speak.
solution will be
Yeah.
single or multiple or no solution.
For no
How?
solution, okay, okay. So for no solution, basically, you can assume for now this parallel lines, right?
Hello.
Yeah. Am I audible?
Yes, sir. Yeah. Right.
Okay, so let's discuss the determinants now. Okay, so determinant of a triangular matrix. So, do you know and can you observe something here? What is the determinant of a triangular matrix? I mean, upper triangular or lower triangular matrix? How can we directly find the determinant?
Sir,
Multiply the diagonals.
Diagonal multiplication.
Product of diagonal elements.
Yeah, multiplication of diagonal entries. Okay, and this is the first property. So from that, we can find the determinant of diagonal matrix as well, right? Okay, because there are only diagonal entries, so we can multiply them to find the determinant. Third property, determinant of product of matrices. Okay, so here it is actually clear from the example. Okay, that this is the A matrix, this is B, and we find the determinant of A, determinant of B, and find find this AB matrix and determinant of AB combined. This is 14. So clearly, this is the product of these two. So determinant has this property. Determinant of AB equals to determinant of A times determinant of B. It can be actually split. Okay.
Yes, sir. Just one question. AB is the just multiplication of matrix. Then we find the determinants, or we can find the determinants AB's in
Yeah,
PV.
so AB is the multiplication of two matrices.
Okay,
So
sir.
then we find after finding AB, suppose this is C is AB,
Yeah.
product of A and B. A and B are individual two matrices, and
Yes.
so then we find this determinant, which is this. Or we can individually find the determinant for A and B, and we can multiply them. This is a property of determinant. Okay.
Yes, sir.
Okay. This is one thing, and this is important property actually. That's why. And fourth property is determinant of A transpose. Okay. So this is the matrix A. Okay. So first I am just telling you the property determinant of A or determinant of A transpose. These are equal. Okay. This is the observation. What is the transpose?
Yes.
Interchange of rows and
Interchange
columns.
the row and column.
Exactly.
Basically, suppose this is the one-th entry. This is 1, 2. Basically, first row, second column, and this is second row, first column. This is second row, second column. Okay. So basically, we will interchange these values. Okay, these values, and then we can get these entries. Okay. So this entry is B is 1, 2. Now we will make this B 2, 1. Okay. So A
So
B.
Aij becomes Aji, right? That's what
Yes, Aij will become Aji. So this is a transpose. So the determinant remain unchanged for this. You can take an example and verify. So should I give an example for this or move to the next property? Because this is very simple. You can
Can
take.
we repeat it again?
So next property. Sir.
Sir, one question.
Excuse me,
What
sir.
we
Can you repeat the previous slide?
Yeah, this property, a determinant of a transpose is equal to the determinant of A. Okay, transpose of a matrix do not change the determinant value. Okay.
Okay, sir.
Sir, actually here one question. What we are
Yeah.
checking through this property actually is why we are doing.
uh, we are studying these properties so that uh, we can uh, we can use them further in the course. Okay. I mean, further in the course means this entire course is actually the foundation for machine learning. Okay.
Yeah.
So in machine learning you will use this transpose a lot. So there you will need these properties that A transpose determinant don't remain unchanged. So there you will use that. When you form algorithms, machine learning algorithms, there these things will be used. Here we are just studying. Okay.
Yes, sir.
Or in this course as well, it will be used in a lot of places. Okay. Inverse of a matrix. Okay. So this is important property. So what is inverse? What is inverse first? Inverse of matrix is, I mean, in 12th class, if somebody remember, can you tell me?
1 by determinant.
1 upon mod A into adjoint of A.
Yeah, adjoint of A divided by this determinant value. Okay, so this is, so if suppose this determinant is 0, that means inverse does not
Inverse doesn't exist.
because denominator cannot be 0. Okay,
Sir, quick question here. What does ADJ of A mean?
adjoint of A matrix. So this will come later. Okay,
Yeah,
what is that?
I haven't learned that concept yet.
I think transpose of cofactor matrix is equal to adjoint of matrix.
Yeah, so it will,
Yeah, we
I
haven't.
think
Yeah.
later in the slides. Okay, so adjoint of A is equal to transpose of cofactor matrix. What is cofactor matrix?
Excuse me, sir.
Yes.
Minors and changing the
Writing the inverse part is not in week one.
Yeah, that's why I'm not discussing this, because this part is in, I think,
Yeah.
week 2. Okay.
Cofactor matrix is -1 raised to ij times the determinant.
Minus 1
Yes,
time.
yes. So the
-1 raised to
transpose of
ij
that would
times
be the
determinant.
adjoint of A.
Okay, basically we'll form a minor matrix, and
Mhm.
then
Yes,
so cofactor of, suppose
minor
this is
matrix.
is ij. Okay, this is the entry, and we first find minor of this. Okay, aij. Okay, and then uh, in minor, if we multiply by -1 plus j. Okay, this is cofactor of this same entry aij. Okay, so this would be some entry in some matrix. Okay, and from there we can find this minor entry. How do we find this? By deleting, suppose this is a entry, so by
By
deleting this
excluding the row and column. Yeah.
okay, so we'll get a minor matrix, and by finding the determinant of that, we'll get this minor. Okay, okay, these things will come later. Okay, basically here we are studying the properties of determinant. Okay, so just remember this. So what is A inverse? This is the definition for A inverse. But more importantly, if you multiply A by its inverse, suppose A and B are inverse, okay, of each other, then this will come as identity matrix. So basically inverse. So I'm not telling this definition right now. Okay, uh, okay, forget about this.
So A
For
times
now,
A inverse equal
for
to
now,
I,
for
right?
now, the second definition of the inverse is uh, such matrix. When we multiply that into this matrix, we'll get an identity matrix. You know what is identity matrix?
Yes, diagonal
Yes,
or
sir.
Diagonal other
Yeah,
one.
this is
No,
a
sir. Please, you can explain what is identity matrix.
identity matrix is only diagonal entries, and they are one. Okay, rest of them entries are zero. Okay, so this is a 3 by 3. Similarly, you can have 2 by 2, 1 1 0 0. Okay, is that clear? Identity matrix. And why we call it identity, there are many reasons, but you can just remember this one. Determinant is one for this. Okay, or uh, or it acts as one. Okay, basically how it acts as one. If you multiply identity matrix in any matrix, we'll get the same matrix, no change, just like multiplying by one. So that's why we call it identity. Okay, is that clear? Identity matrix. Okay,
yes,
so
that's clear.
yeah, so for inverse, the definition is uh, suppose this is matrix A, this is matrix B. We multiplying, we are getting identity matrix. Then we can say A and B are inverse of each other. Okay, inverse matrix of each other. Okay, so what is the effect on inverse? What is the effect on inverse? So AB is equals to identity matrix. Okay, A and B are inverse of each other. We can take determinant both sides. What is the determinant of identity matrix?
1.
One.
One.
Well,
And we can split this, okay, from the previous property. Okay, so A time determinant of A times determinant of B equals to 1. Okay, then we can say determinant of A is equals to 1 upon determinant of B. And B is what? Inverse of A, right? So inverse of A, so we can represent that inverse of A. Okay, so this is the relation we got. Is that clear? So basically, uh, inverse is the determinant is also the reciprocal of the mat determinant of the matrix. Okay, is it clear? This property, inverse one.
Yes. Yes.
Yes, sir.
What is the determinant of a to the power n?
Determinant of a the whole power of n.
Yes, n times. Okay, n times these are this is okay. So we can actually take determinant. Then determinant can be split out dot n times. So this is the determinant of a to the power n. Okay, equals to, okay. This is the one more property of determinant. Yeah, determinant of a transpose a. What is the determinant of this?
A square.
Determinant of A square.
A transpose, and A transpose and A are same. So determinant of A square is this property. What is the determinant of this?
Determinant of A.
Determinant of A.
Sir, will you just scroll up?
Okay. Okay.
Sir, will you explain this? Yeah.
Yeah. This is we are finding determinant of this quantity A transpose A. Okay. So we can split the determinant. Okay, for both by the property discussed above, and
Yes.
A transpose determinant of A transpose is equal to determinant of A. So we can replace this by determinant of A. So now we get determinant of A square. Okay.
Okay, sir. Thank you.
Okay. So determinant of P inverse AP.
Determinant of A.
This
Sir,
is
what is the P here?
any matrix, invertible form, okay? Non-singular
Okay.
matrix. Uh, okay, so we are splitting the determinant values for them, and we know this. We can replace this P, or maybe this one, this determinant of this by,
1 by P.
okay, this will be cancelled out, and we get determinant of A. So property is determinant of this quantity equals to determinants of A. Okay, if we multiply uh, pre-multiply by some invertible matrix and post multiply also by the same matrix, okay, then we can there is a no effect on determinant value. Okay, so these are properties of determinant. So most important properties are this one: determinant can be determinant of a b equal to determinant of a times determinant of b. This is one property which is very important, and there are these properties, they are coming now, very important, like row operation. Okay, so what are row operations that we can apply in finding the determinant? We can switch two rows, okay, or two columns. We can multiply a row by any number, okay, non-zero number. With this operation we can do, and replace a row by multiple of another row added to itself. Okay, these are the three operations. What are these operations I'm discussing? Okay, so first is switching to rows and columns, or columns. Okay, I mean, no, we cannot switch rows by column, because that would be transpose, right? If we switch all the rows by column, and then that would be transpose. We are talking about, suppose this is 1 2 3 1 0 2 3 1 2. Okay, any matrix, and suppose we are finding determinant for this. Okay, so what we can do, we can switch any two rows. Suppose we are taking first row and second row, interchanging them. So 1, 0, 2. This is the second row. I'm writing in place of first. Okay, first row is 1, 2, 3, and 3, 1, 2. So I have changed these two rows. Okay, what is the effect on determinant? If this is A, okay, these are two matrices. Okay, then if determinant of this matrix is this, then determinant of this matrix would be negative of this. Okay, this one, this one. Okay, so effect is negative sign. Okay, is that clear?
Yes, sir.
If we interchange
Yes,
any
sir.
two, similarly, if we interchange any two columns, same effect will come. We on the determinant negative sign. Okay, so suppose if we change the two rows again, what will happen? Again, there will be a minus.
Positive.
This will become mod if we change any two rows again. Okay, any of the two, suppose these two, we can interchange.
Means sir, when we find the determinants of A, like the method of finding of determinants, the
Mhm.
in the left hand side, that suppose determinant of A is 3, and
Mhm.
when we calculate the right side of determinant, it will be minus 3. Always, it will be
Yes,
always minus.
it will be a good exercise. Just quickly check. Suppose I for 2 by 2 matrix, I'm checking 1, 2, 3, 4. Okay, this is a matrix. Okay, what is the determinant of this?
-2.
Minus 1.
Minus 2, right?
Minus 2.
Minus 2, right? So if we switch two rows, suppose 3, 4, 1, 2.
Yeah.
What is the determinant of this? I
X.
mean, it should come plus 2, right?
It will
Let's
be
check.
2.
Yeah.
It is coming. Indeed, it is.
2.
So it is verifies property. Okay, or you can now change two columns like 4, 2, 3, 1. Interchanging the first and second column. What is the determinant now? Again minus 2. Again
-2.
minus 1. So basically, this is the first property says. If you switch any two rows or column, negative sign comes. Okay. First property is clear,
Sir,
right?
sir, quick question.
Yes.
Instead of swapping the rows,
Hmm.
if you just swap the elements within a row, is there any effect on the determinant? Say,
How will you do that?
so for instance, if you
I'm
for
taking this
A1,
matrix.
instead of A11 you put A12, and instead of A12 you put A11.
This is not a valid operation. These are the
It's not a
three.
valid operation. Okay, so that
Yes.
there will be no effect of changing the
No,
elements
no,
within a
no.
row.
There will be effect. There will be effect. Matrix would be changed. Determinant would be changed
Okay,
completely.
but there's no property like that.
Yeah, this is not a
Okay,
valid operation. That
okay, good. Thank you.
would be a different matrix. So basically, suppose you are interchanging these two values, 1 and 2, then you have to change these values as well, corresponding. Basically,
Okay,
entire rows and column can be switched. Okay.
okay, got it.
Okay. Second property. Second property says multiply a row by a non-zero number. What would happen?
T times of determinant
The
of.
determinant is divided by that, multiplied by that number.
Yes. So if we multiply any row, suppose this by k. Okay. So if we find the determinant of the previous one, it would be AD previous matrix. Okay. Without multiplying by k, it would be AD minus BC. Right. This is the now if we find the determinant of this one, it would be k times AD minus k times BC. So k come outside, AD minus BC. So basically, whatever is the determinant, now it is k times. So just observe this, just multiplying one row by some scalar, the entire determinant is multiplied by that scalar. Okay. So this is the property I'm writing.
Sir, you said that if we interchange every row to the every column, it will become transpose.
Hmm.
That is not correct, I think.
Uh, I mean, you are saying
If we
What was this
interchange
question?
every row of matrix to the other's row, then it will become transpose. Then it is not correct.
where did I say that? It will not
So
only
starting
interchanging rows only, right?
in the starting sir, when you are discussing
No.
that theory.
In the starting, I said, suppose this entries AI A11, A12, A21, A22. Okay. So if I interchange these two values, okay, so A11, A1, I mean these two values, and
Changing row to the column, then it will become the transpose.
yeah, that is a simplified form. You can this A11, A12, and A21, A22. Yeah, this is actually transpose.
Kundan, the diagonal entries would be same. The other entries would change.
Yeah.
No, that part
Suppose
I understood means
this is
I am
one,
asking.
this is 1, 2, and now it is 2, 1. Okay.
Yes,
I mean,
sir.
this value comes here at the place of 1, 2, and 1, 2, 1 comes at 2, 1. Okay.
We can say no, sir. If we change row to the column, then it will become the transpose.
No, I didn't say that. If you
Sir, we can say that like that. That its row is that 1, 1 and 1, 2,
yeah,
and
yeah.
make,
Every row,
make it to the
yeah.
column.
If we take every row and make it to column, corresponding columns, then it is a
It will
transpose.
become the transpose.
Yeah, but that definition comes from here. We interchange these entries. Okay, these order. Isaac.
Okay, sir. Thank you.
Okay. Second property is multiply by some non-zero number. The entire matrix, entire determinant would be multiplied by that number. Okay, these two properties clear.
Yes, sir.
Okay. Third property is
Yes, sir.
replace a row by multiple of another row added to itself. Okay. Then determinant would be unchanged.
Unchanged.
Okay. So what is the meaning of this?
Sir, scalar multiplication to a column is not valid.
Valid. So
So the same property would apply, no?
yeah. So if we multiply this by k, suppose second column by k, second entries, this is equals to k times a, b, c, a. Okay, we can take common from one column or one row. You can take any constant column scalar. Okay.
Okay.
Scalar multiplication of row by a constant t. Okay, this is the second property. Okay, so we can write this as this is suppose k times b, k times b. This is equals to a, c, b, d times k. Okay, this is the property. Third property is where? So I'm explaining third property here. Okay. Suppose this is matrix A, and what we are doing is, okay, we are taking different matrix A, B, C, D. Okay, this is A, and if we multiply the first row by T, so T A, T B, C D. Okay. Now what will be the determinant? T times A, right?
T times of it.
Now after multiplying the first row by T, we are adding the adding it in the second row. So what matrix do I get? C plus T A, D plus T B, and A B. This is the matrix I get. So by applying this third operation, I mean taking any matrix, taking any row or column, multiplying it by some scalar, suppose t, and adding it into the another row or column. Okay. I mean, just remember this. Apply one at a time. If you are multiplying in rows, then you can add that row into another row. Okay, you cannot do that multiplying some constant in row and adding that row into some column. You cannot do that one at a time. Either apply it on column or on rows. Okay. In this case, if you find the determinant of this, can you find the determinant of this? Let's calculate. Okay.
Yes. A into
A times t plus tb minus b
ID
times
E into C
ta.
plus T
So we get ad plus
plus
ab
80.
A
times
PT.
c minus ab times t. Okay. So
Nothing is getting cancelled.
yeah, this one is getting cancelled, and determinant comes as ad minus bc, which is determinant of a. So see, determinant is unchanged by applying this operation, while when you applied this operation, determinant is changed. Okay. So this is another property. Determinant of this is equals to determinant of a. Property 3. All the three properties are clear. This one, switch rows, what happens?
So little bit confusing third property, sir.
Third property is confusing. I derived, right? AB, okay, A, B, C, D, and determinant of this is this, and when we multiply the first row by t, the determinant becomes t times a. But if we multiply the first row by t and add into the second row, okay, and make this another matrix, and when we find the determinant is unchanged. We have calculated it. Okay.
Got it, sir. Got it. Thank you, sir.
Just try to remember this. Or we same thing. We can do it. Do on column as well. Okay. Find the determinant of A and determinant of B. So what is done in these two matrices? So this is A, and we are multiplying the first row by 2, okay, and the last row by 2, and the middle row is also okay. So entire matrix is actually multiplied by 2. Okay. So what is the determinant? Can you tell me quickly what would the determinant? So suppose determinant of A. What is
Determinant of A
the
is 2.
It's a double of determinants of A.
what is the determinant of B?
16.
Who said double?
4, sir.
No. See,
8, right?
we are multiplying the first row by 2. Okay. So even from the first row, determinant would be multiplied by 2, and then second row also. So now
2
the
into
determinant
2
will be
into
2 times,
2.
and then the third row. So it will be
2
2
cube into
times
2 into 2.
the determinant of A. So which is 8
16.
times determinant of 2, which is 16. Is that clear, everyone?
No, sir. Can you elaborate it?
Okay. I mean, which part you have problem?
Just
Multiplying
why
to
we
every row.
just 2 to the power q. Can you
Can you see
explain?
this? This first row is multiplied by 2, and second
Yes.
row is multiplied by 2, and third row is multiplied by 2.
Yes.
What is the effect of multiplying first row by 2? 2
It's
times, right?
2 times.
And then what is the effect of multiplying second row by 2?
For
2
every
times.
multiplication, we are just multiplying 2.
Yes.
Suppose here fourth row is there, then 2 to the power 4.
No, it cannot be there because then the order would be different, right?
Okay.
If the both of the order will be same, then
Yes. Then we can take. So basically, this is 3 by 3, right? You're talking
Yes.
about 4 by 4, right?
Yes,
Yeah.
sir.
Same thing actually replicate there also.
Okay,
Okay.
sir.
Okay, so
In determinant, it will be always a square matrix.
Actually, in 4 by 4, 4 by 4 matrix, generally it is difficult to calculate determinant. Okay. Only
yes.
up to 3 by 3 matrix we can find determinant easily.
Yeah.
Okay.
It will be cursive.
From there on, there are other methods to find determinant. Okay, which you will study. I mean, I'm not sure, but you can search on web. There are
Yeah.
many.
Okay, sir, got it.
But for the similar scenario, can't we calculate in the same way like 2 power 4 into
Yeah,
determinant of A?
these operations will be applicable. I mean, this is the properties of determinant, not the 3 by 3 determinant or 2 by 2 determinant.
Okay.
These properties are for determinant. So even n by n matrix is there. Uh, there also the same properties will be hold. Okay, no problem. Now this observe this. Uh, so that property actually there in the previous question you have observed what has happened there. Actually, the entire matrix is some alpha times a, or to be specific, it is 2 times a, right? It was 2 times a. So when we find the determinant of both sides, so when we taking outside any constant out of the determinant, what will happen? The order.
The
Which is,
total order of
if it
determinant.
is a three matrix, so basically in general, if I talk about B is equals to alpha times A, then determinant of B would be power n determinant of this is the property. What is n here?
Order of the matrix.
Three.
Order,
Three.
order,
Order.
of, order of
Three.
the
Order.
matrix. Okay,
Order of the
yeah. In general, I'm just saying order of the matrix, right? Okay.
Yes, sir.
So can you solve this exercise? Determinant of it. Take some time and tell me the answer.
8.
8.
8.
Eight, sir. Eight answer.
Anyone, any doubt why the k is 8? Okay. So multiple of row and column can be added in another column without changing the determinant's value. Yeah, this is the third property. I have already discussed this. Okay.
Yes, sir.
This
Sir,
is
will you
matrix.
explain the second one?
Which one? Second property.
Yeah.
Multiply a
Not
row by
that, sir. Question, sir. Second question. Det of 2A. The above one. Yeah.
this one. This one. Okay. Yeah. So determinant of 2a is k times determinant of a. So determinant of 2a would be 2 to the power, because this is a 3 by 3 matrix, right? So 2 to the power 3 determinant of a, right? And this
Yes,
is
sir.
2 to the power 3 is what? K. Okay.
Okay.
That is 8.
Yes, sir. Thank you.
From this property. Okay. This one or this one.
Yes, sir. Thank you, sir.
These are two matrices. What is the relationship
Sir,
between A and B?
I
Yes.
have a doubt in the property number 3. What
Hmm.
if we multiply a row with another?
Multiply a row with another row.
Yes.
No, property says multiply a row by constant and then you can add or subtract in any other row. Okay, this is the property. If you multiply two rows, it would be a different matrix. This is not the valid operation for determinant. Okay, it will change the matrix basically.
Okay, sir.
Okay.
Sir, how can we multiply two rows? Maybe we can scale a row, right?
Or maybe corresponding saying like A,
Not multiply.
B, C, D. So if you C saying if you like A, C, B, D, C, D. Okay, so you are basically multiplied these two. I don't know what to say this. Okay, So this is basically Shiva's
Okay,
talking. So in
only
this case,
things.
this is not a valid operation. Yes. Yeah. Somebody asking something. This is not a valid thing. Okay. Okay. These below you have given two matrices. What is the relationship between A and B, and what is the relationship between determinant of A and determinant of B?
Determinant.
Determinant are same.
Determinant is same.
Determinant is same
Okay. Why it is same?
because
Because in B, the
it's a row
first
operation basically.
row
Addition
It's
operation
added to the first row.
added to the first. Yeah, k times the second row basically. The first row is k times the second, the B matrix.
2 times, then added to the first.
Second row multiplied by 2 and added to the first row.
Yes.
Yes. Yes. This is the correct. So basically, in this we are applying operation.
R2 plus R1.
Row 1 is changed. Row 1 plus 2 times R2. Okay. So when you do this, what so you multiply this by 2, we'll get 6 and 8. Okay. And then add, we'll get a matrix 7. Okay. 1 plus 6. Okay. I'm writing 1 plus 6 and 2 plus 8, and here 3, 4. Okay. So this is the basically determinant we are calculating. So because this is the third property, and the determinant will be unchanged. Okay. So you can calculate and verify. Uh, so determinant are same basically. What is the determinant of this matrix?
0.
0.
1, 2. Can you observe anything here?
Sir,
Yeah,
pattern.
R1 is of R2.
2 times of
R5 is of R2.
R1 is half. Sorry, R2 is the
Okay,
2 times.
we can take 2 common from the second row, or we can take directly out of the determinant, right? We can do that.
Yes, sir.
Now these are 2 rows, right? So we can apply this operation row 1 minus row 2. Okay, and we are replacing row 1, right? So we will get 0, 0, 1, 2, 2 times. Okay, and now we can calculate determinant of this, because any one row is 0 or any one column is 0, the determinant is 0. So 2 times 0 is 0.
Yeah,
Okay.
if we calculate the determinant directly without doing all this operation, the resultant value will be the same.
Yes.
Yeah.
Okay, but we do it for simplification. Sometimes, suppose this is a 3 by 3 matrix, and it's not easy to find the determinant. Then what we do, we apply these operations, these 3 operations, and try to create zeros, so that we can easily find the determinant. Okay.
Yes, yes, got it. So,
What is the observation here? If a
Sir,
matrix contains, yeah,
if two rows or two columns of a matrix are same, so its determinant will be zero, no?
yes, yes, yes. Okay, this is the actually property. If a matrix contains the row column multiple of another, that the determinant is 0. Multiple means if they are same, that means they are multiplied by 1, right? If any number, if one row is k times the other row, or one column is k times the other column, then the determinant is 0. Okay. And
Yes.
why this is the case? Because we can take k common and make the column same, right? Okay. Now this is coming determinant in terms of minor and cofactor. Okay. So what is minor? So definition of minor is when we minor is, I think, already cleared. We can take any matrix, and so minor is for every entry. So for suppose m I j, then we will delete I and ith row and jth column.
yeah.
Okay, corresponding row column basically we'll delete, and then the remaining matrix, the minor matrix, we'll find the determinant. That is the minor. Okay. Okay. And what is cofactor? Cofactor is this minus times I plus j, and this is cofactor. So this is the relation basically. So this is the A matrix A11, A12, A3. We can find the minor of suppose for one entry. First one I'm finding, or maybe second one. Okay. So I'm finding minor for A12. What is the minor for this? Determinant of, so because we are finding minor for this entry, so delete this column, this row. Okay, so we get these four entries. So we can write them: A21, A23, A31, and A33, and then we can find determinant of that. This is the minor. And what is cofactor? Cofactor of A12, we can take -1 and 1 plus 3, 1 plus 2, these two. Okay, times minor of A12. Is that clear?
Sir, 1 plus 2 to the power. Can you explain?
Yeah, 1 plus 2.
Yeah.
1 plus 2 because we are finding this 1 2 with entry. Okay, that's why.
Okay. Okay.
Basically the row number plus column number. Okay.
Okay. Suppose we calculating for A13, the power will be 1 plus 3.
Yes, exactly.
Okay.
Okay, so this is the slides now. It's completed. Now we can move.
Sir,
Yes.
if in any matrix either a row or a column have the same entity, then the value of the determinant is 0.
Yes. You're saying this, right? If I understood correct. Suppose uh, A, A, and B, C, D, E, F, G.
Yes,
Okay,
sir.
okay. Yeah, you're talking about this?
Yeah.
No. In that case, what would happen? We can take column A outside, and we can have 1, 1, 1, B, D, F, C, E, G. So definitely, this is not necessary that it would have determinant 0. Okay. Not necessary. I can write this.
Either two in determine rows or column will be the same entity,
Yeah.
then also this statement is wrong.
No. Then suppose this is also A. So now two columns are same, right?
Yeah,
Now determinant would be 0.
but not for one row or column.
I not necessary.
Okay, sir.
I mean, you are saying all the entries in one column are same, not necessary that be 0 determinant. Okay.
It can be, but not necessary, no, sir?
Sorry.
Yeah, it can be 0, but it's not necessary, right?
Yes. It is not necessary. Maybe suppose these we don't know about these entries, right? Suppose maybe this third column is just 0 0 0. Okay. It could be the case, right? In that case, suppose this is 0 0 0, and this is 1 1 1. Now these two columns are different, but still the determinant is 0, right?
Okay, got it.
So this is the slides I had to cover from the previous session. Now let's come to our session. Okay, so if you have any doubt in week 1, you can ask now from activity questions.
Yes, sir. Activity number.
Sir, my 1.3.
Yeah, activity 1.3.
Question number 7, 1.3.
Sir, my question number 1.
Okay. You try to ask question one by one. Okay. Okay, so I'm discussing the question number 1. Consider a linear equation, okay, and answer the questions. If the matrix representation of system 1 is X equal to B, okay, and then which of the options is correct?
Sir, option number 1 and 4.
1 and 4.
Yes, sir.
Yeah, then you are, I think, replying or you are asking same.
Sir, question number 6.
Sir,
Okay,
my question number 2 also.
no, but you answered this, and why did you ask this?
Sir, my first one is clear, then second one is fully doubted.
Okay.
B is given right at 105.
Excuse me?
Okay, any question, any doubt in this question number 1? No, I guess, right?
No, sir.
Okay, next question, question number 3. Okay. Here we have to find the correct options. Think A as a 2 by 2 or 3 by 3 matrix and B accordingly.
Sorry, screen is not visible.
My screen is not visible.
It is visible, sir.
Visible, sir.
It's visible.
Share the entire screen. So what about the first option? Every system of linear equation has either a unique solution, no solution, or infinitely many solutions. Is this true?
Yes, sir.
Yes, that's true.
Yes, sir.
Yes, sir.
Because it is covered all the possibilities, right? So one of them is correct, right? So this is. What about the second option? If each equation of the system of linear equation is multiplied by non-zero constant c. Okay.
It is wrong.
Then the solution of the new system of the equation is c times the solution of the old system. What is the solution? I mean, okay, let me share my this note, one note. Okay, live systems. Okay, so what is solution? Suppose this is a system ax equals to b. What is a? A is a matrix, okay, of
Coefficient matrix.
some order. Suppose m cross n. Okay, what is x?
A variable.
Constant.
A
Variables.
a vector. Okay, a vector. What is the difference between vector and the matrix? Vector is one.
Vector is a column or a row.
Yeah, vector is one dimension, and matrix is basically 2 dimension or more. Or okay, matrix is 2 dimension. So x is because these are multiplying, so clearly this n cross 1. Okay, so a would be like this, m cross n. What is a? Coefficient matrix. What is n? A column vector of variables. Suppose there are x, y, z, 3 variables. Okay, if it is a 3 by 3 matrix, it can be it need this coefficient matrix need not be a square matrix. Okay, m and n can be different. And what is b? B is also a vector, but it contains constants. Is that clear now?
Yes.
Okay. So what is the solution? Solution is these values of these variable x and y that satisfy this equation, right? Okay. So what is x? If you multiply a is invertible, suppose. Okay. Suppose a is invertible, then we can multiply both side by pre-multiply by a inverse. Then this will become identity matrix, and identity times would be x. This would be a inverse b.
A inverse of B.
So what is x? I already told this vector. So basically we have solution. I mean, we have some value for x1. Suppose this is small x, small y, small z. So we will be having some values, right? Which will be taking coming from here. So first value will be this, second value will be this, third value will be this. So basically, this A inverse B is the solution. Okay, but it is possible only when the A inverse is exist. A inverse means this matrix is invertible. That means determinant is not equal to 0.
Non-zero.
Determinant of A. Okay, so this is the condition for having a solution, basically. So what was the question? Each equation has this solution. Okay. Second option is if we multiply uh, each equation by C, then what will happen? The matrix A would be multiplied by C, right? This matrix A. Okay. Is that clear? When we multiply each equation by C, then B also multiplied by C, and this is also multiplied by C. Okay. So in that case, what will happen? We can cancel out C from both sides, and the solution will be unchanged.
Unchanged.
Okay. So it is saying it is changed. It will be C times the solution of the old system. So it is not true. What is the third option? Third option is Ax equal to B is a system of linear equation which has a solution. Then system of linear equation C times Ax equals to B, where C not equal to 0 will also have a solution. Is that true?
Sir, can you
Yes,
explain this
it's true.
a
No,
little?
sir.
So basically it is saying Ax equal to B has a solution. That means determinant of A is non-zero.
Non-zero.
Yeah, means true. Both the true.
Then the system of linear equation C times Ax will also have a solution, right? Because C is non-zero, right? There is no problem. And what will be the value of that solution? C times
Sorry,
Ax.
which one you are asking?
What is the solution of this? I mean, it is saying solution exists or not. C not equal to 0. Then we
Yeah,
can
it's a solution for the system of linear equation Ax equal to B.
so B upon C we can say. So X equals to A inverse B by C. C is non-zero, right? Solution exists. Any doubt in this question?
No, sir. No,
Okay.
sir. No.
The
No,
option is
sir.
say if Ax equal to B is a system of linear equation which has a solution, then 1 by C 8x equals to B, where C non-zero will also have a solution. Yes. Okay.
So here we suppose we are considering C as a real number, right?
A real number, yes, or non-zero real number.
Scalar like a real number, something, right?
Yeah, non-zero real number. Yes.
Okay, okay, sir. Both are true, sir. No doubt.
Any other question from the activities?
So question
Fourth
number
one.
Sir,
4, sir. 4.
Okay. The plane 1 and plane 2 in figure correspond to two different linear equations which form a linear system of linear equation. Okay. Yeah. So are these parallel?
Yes,
yes.
sir.
They are parallel.
Yeah. Then no solution. Okay. No solution means there is no common point between these two planes. Okay.
So means there is no common point where
Two
if we draw a line with this equation, there will be no common point.
Yes. Yes.
No intersect point.
Okay.
Sir, I have a question. Can I ask?
Hmm.
Sir, next
So
6
basically,
number, sir.
if sir, in this question, question number 4, if there
Okay.
if two planes are touch each other, then there will be infinitely many solutions, right? Because
Yes.
it cannot
They will
be.
intersect. Yeah, intersect at a line.
Yes, yes, yes. So there will be infinitely many solutions, right?
Yeah, the whole line will be common, so infinite.
Okay, okay.
Okay. If these are two line only, then if they intersect, because there are only two planes. So what if will your statement true when if there are three planes?
No,
Oh, no.
in that case,
No,
I
there.
hope it will be have unique solution, right?
Uh, no. In,
It will be same. No?
suppose
It
there
will
are
depend if the planes are
No.
parallel or
suppose there are three planes and two plane are intersecting, but one plane is not intersecting. In that case, a no solution case.
No,
Okay.
sorry.
But
Okay, okay,
if three of the planes are intersecting at a single line, then again infinite solution. Okay.
okay.
Sir, I have a doubt.
Can I ask a doubt?
Yeah.
So my doubt isn't solved with us question number 10.
Sir,
Sir,
in this question number 6, sir.
sir, before that, can we go to question number 3 again?
Okay. Yes.
Sir, my doubt is, if we have a system of linear equation, we can multiply that equation to get a new equation. So here we are multiplying it with the constant c. So b should also be multiplied with c, right?
In which option? Last option?
No, third option, third and fourth option. So in
Third.
third option, it should be bc, and in fourth option, it should be b into 1 by c, right?
But it is saying that equation which has a solution will also have a solution. Basically, it is asking about existence of a solution. That's why this option is true. It is not saying the solution is same as the previous one. Previous means ax equals to b. Solution is definitely different from the solution of ax equal to b.
Mm. Moreover, we have given the equation. The equation is given.
Yeah. So in the second option, what was happening? We are multiplying c both sides. Okay, both side means we are multiplying b also with c. Okay, but here we are just multiplying this left this coefficient matrix only in the fourth option. Okay, is that clear? Whatever you are trying to ask.
There's still some doubts there, but I'll clear it on my own. Thank
Yeah,
you.
you can ask. You can ask. I have time.
Sir, then are you saying that if I multiply only the coefficient with the real number or with the fraction, there will be a new system of linear equation which will have a unique solution?
No. Actually, I'm not getting your point. Can you repeat?
Sir, so the first system of linear equation is ax is equal to b, and the
Yes.
second is c ax is equal to b. So my previous question was, when we are multiplying one side by c, the other side should be also multiplied by c, right?
No. Not at all. I mean, it is not necessary. You are asking about necessity, right? So suppose we can multiply by c just for making the question. Why we are multiplying by in b also?
I,
I mean,
I think he's asking about balancing the equation on both sides when you
Yes,
multiply
sir.
c on
Yes.
left hand
yeah,
side. So I don't
for
think we're
balancing,
balancing here.
yeah. If we multiply c both
But
sides,
in check,
then the ax equals to b. Same system will get again. Okay.
So we are creating a new system of equations with a unique solution, right? By multiplying with c.
Mm-hmm.
Okay.
Yes.
So the
So
b.
basically, if this has unique solution, and c times a x b also have a unique solution.
Okay.
Okay.
Okay. But sir, another doubt: does the b change or is it the same? Because when we are
it's C.
multiplying, b should change.
Yeah, it will be changed. What is the new? It would be like ax equals to b upon c now.
B by
This
C.
this is new. Suppose b dash.
Okay. Okay.
Okay.
Thanks.
Okay. Or you can say
So,
you can say
mm,
you can multiply every entry by c of a. Then in that case b will remain unchanged. So both way is possible. This question basically are not making any improvement here.
Sir,
Okay.
The question number 6, sir.
sir,
Hmm.
Sir, have we
sir,
completed
what?
with AQ
Sir,
1.2, sir?
check solve with us question number 10.
Sir,
Yeah, one by one, please.
Question
Yes.
number 6, sir, in this activity, same activity.
Yeah, this is the system.
Yeah.
Choose the
In this,
correct option.
just, sir,
Uh,
what is the difference between last two option? The system has infinite many solution, infinite solution k equal to -3 and d equal to -6.
yeah, this is a different. Clearly, D is in the third option. D is 6, and the fourth option, last option, the option is D -6.
We
Right?
have
It's
to
the
check whether these like k value of k and value of k is suitable for a particular option. Like the system
okay,
has
okay, okay.
infinitely
You
many
are
solutions.
in what way you are saying? I mean, I think you are saying just what is the difference. I think both options are same. That's what you are saying, right?
Yeah, yes, sir.
Not same. You can see D value of D is different.
Okay, got it, sir, got it.
Sir, will you
Next.
explain fifth question in this activity?
Sir, question number 7 in this activity.
And
Okay,
sir,
let's
can you explain the
first.
question number 7 just? Okay, what is asking
Okay,
about question number
okay.
7?
After this, I will take. So this is the fifth question. Okay, three cases. Which option you have doubt?
Sir, actually figure C, sir. Yeah,
Okay,
I just
C.
have doubt. Yeah.
Yeah, figure C. So there are. This is just one line.
Yes, sir.
So I mean, which option if you doubt why this option is correct and why this option is wrong, I will tell you which option.
Sir, why doesn't become a no solution? Like, yeah.
In the last option,
Yeah, yes, sir.
figure C represents the system of linear equation has no solution. So why will be no solution? There are only one equation, right?
Infinite many solutions. Both lines are overlapping each other, so there would be infinitely many solutions.
Yeah, there are two lines, right?
Okay, okay, sir. I got it. Thank you.
Okay.
sir, sir,
Just
Question number
explain the
7, sir.
question number 7. What is
sir, sir.
Okay. In 7, yeah, I'll come after this question. Okay.
okay,
So
okay.
let x1, x2 be solution of the system. Ax equal to b. Okay. Yeah, which option I should explain?
Actually, sir, not
One question,
exactly.
sir.
I am not understand the question what he's asking.
Okay, okay, okay. I'm explaining this question.
Yeah.
Okay, so this is the question, and here let's take the first question first. So x1, x2 are the solutions, okay, for the system. So what does it mean is a. So basically there are two solutions given. Okay, a x1 equals to b, and this is satisfying the system, and a x2 equals to b. This is also satisfying this system. Okay. Now it is asking whether a x1 plus x2, whether this is also satisfying or not. Okay. So let's check ax1 plus ax2, and this is this is b, this is b, this is 2b. Okay. This is also b, this is also b, so this is 2b. Is that clear?
Yes, sir.
So so x1 plus x2 is a solution of this system. Ax equals to 2. This system is has the solution x1 plus x2. So that's why first option is not correct, second one is correct.
Correct. Yes, sir.
Okay. And for x1 minus x2, similarly you can check
Yes, sir. It will be 0 under.
x1 minus x2, and so here it will be 0, right? So this is the solution. X1 minus x2 is the solution of this system.
Yes, sir.
Sir, could you explain question number 8 in this activity?
Okay.
So have we completed with previous activity, sir? 1.2.
1 point, no, not completed. You can ask any activity question. Okay.
Okay, okay. Actually, I have doubt in
Nobody
activity
actually asked,
1.2, sir.
yeah, nobody actually asked from there, so that's why I took this. Okay,
Sir,
so
what is the sir? My
let,
question.
let me complete this activity first. Okay. Yeah. So
Okay, sir. Yeah,
now
yeah,
which
please. Activity by
Question
activity,
number
sir.
8, sir. Sir, in this activity.
the slide bar is actually what happened. Question number 8. V is the solution of the system of linear equation. Ax1 equals to b and ax2 equals to b. Which of the following are correct? Okay, so let me take the screenshot. Yeah, so in this question, which option you have doubt, or should I explain all the options?
Explain everything,
All
sir.
the options, sir.
Yeah, basically V is the solution of this system. So V satisfying this means A1 V equals to B. This is satisfying this, and this system is also satisfying V. Okay, no problem. Now let's check the first option. V is the solution of the system this. Okay, so let's check. This system is A1x plus A2x equals to B. So A1x is B and this is B. So clearly this is B and here it is coming to B, right? Not satisfying, first option. But second one will be satisfying. Same question, I guess. Okay.
Yes, sir. Yes, sir.
I've
Done.
discussed it already. I just didn't read those, so that's why I took this. Okay, next question. These two questions are same basically. This question number 8 and question number, I think, which one? 7, yeah. 7 and 8 are same. Yeah, next question in this activity.
Sir, my doubt.
Okay. What is the
Sir,
doubt?
sir, what is the difference between question number 2 and question number 4?
Question number 2 and question number 4. Question number 4 is this, right? And question number 2 is this.
Sir, what is the difference between their number of solutions or no solution?
Number of solution, no solution.
Sir means many solutions, no solution, or unique solution. That kind.
Yeah, unique solution means only one point is satisfying all the equation in that system. Or infinitely many solution means infinite points are satisfying.
Okay, sir.
Sir, can we go
Sir,
to
in the
activity 2?
Or if you want to visualize, you can say suppose I think in the, yeah, okay, here one diagram, I think here, yeah, this one. These are the diagrams. So these are two equations, suppose, right? So they are intersecting exactly at one point. That means they are giving unique solution. Okay, and these two lines are actually coincide. They are on top of each other. So they are actually meeting at infinite points. And now they are not meeting anywhere because they are parallel. That means common solution is 0. I mean no solution. Okay.
Okay, sir, got it.
Okay.
Sir,
Yeah.
in the question number 4, can
Hmm.
we say that in 3D plane we'll never be able to find the unique solution?
No. You cannot say that.
But in which scenario we'll find the unique solution in 3D plane?
Okay. 3D plane. I mean, you're talking about 3 planes, right? So let's take 3 planes. Yeah, your question is interesting. Let's think.
Yes, because in 2D plane we can visualize line is crossing, there is unique solution, and not touching is parallel, there is no solution, and overlapping then many solution, infinite many solution. But in 3D I cannot visualize it, how it will happen.
Okay. So suppose this is the third plane. This is z-axis. Okay. This is coming outside. Can you are you able to visualize?
Yes.
Okay. So this is one line. This is an xy plane. This is another line. This is an yz plane, and some other line. Suppose this one. Okay. So basically, these 3 lines, they are not in 2D, right? I mean, one line is in some other yz plane, some line is xy plane. So basically, these 3 equations are in uh, uh, are in a 3D structure. Okay, R3, and still because they will meet at one point, right? So it will give unique solution. If you're
Okay,
if you're saying if you're particularly taking only planes, then definitely two plane will intersect at a line. So definitely it will give infinite solution. In that
yes.
in that case, it will either no solution or infinite solution in case of plane.
True. Understand.
Yeah, but plane one line in case you can find unique solution. Okay, so how it look like? One plane, one line equations. So you can do x plus y plus z equals to 3. So this suppose this is one plane and equation also. Equation of a line is x plus y equals to 1. So this is line and this is plane. Okay, plane is in 3. This is in 3D, right? Because z coordinate is there. So this is in 3D and this is one line. Okay, so we can find actually solution. Either it is no solution or whatever. To calculate. Okay. Anyways, any question, any doubt in this activity?
Excuse me, sir.
Yes.
Can you explain the second question in this activity? How it get unique solution?
This is the part of this question, right? Okay. Unique solution. You can solve this system. Okay. Should I solve this?
Yes,
So,
sir.
is there any particular property for?
Yeah. This is an interesting question. I mean, you are saying that is there any method to solve the system, right?
Yes.
Yeah, there is a method. It will come in, I think, week 2 or 3. Gaussian elimination method. Using that, we can, or just for sake of solving, you can do this third equation. 2x2 is equal to 5, right? Then x2 is 5 by 2.
Yeah.
X2 is 5 by 2. And what is x3? X3 is x1 from the second equation, right? X3 is equal to x1, right? From the second
Yes.
equation. Is that clear? Yeah. So now you have x3, which is x1, and now you have x2, which is 5 by 2. You can take value of x2 and x3 uh, and put it in equation number 1. So x2 is 5 by 2. So 3 times 5 by 2, that is 15 by 2. And x3 is again x1. Okay, then so it would be minus x1. So you can basically find the value of x1, and now you have value of x1 and x2. You can put in the second equation and you can find the value of x3, and this is how you can have the solution x1, x2, x3. Okay. Okay, should I solve this or
Hello,
Yes, sir. Can you?
sir. Excuse me, sir.
yes, yes.
Please mute him.
One
Am I
minute.
audible?
Yeah, you are audible, but just 1 minute. Okay. Okay. So these are the three equations. What I'm saying is, you have x2 equal to x2 equals to 5 by 2, right? And from second equation, you have x3 equals to x1. From first equation, you can take the value of x3 and so minus 2x1 plus 3 times what is x2? X2 is 5 by 2 and plus x, what is x3? X1 equals to 1. So now x1 and this it minus x1 and 1 minus 15 by 2. So this is minus 13 by 2 minus x1. So x1 equal to 13 by 2. Now you have x1 and you have x2. You can put it. Uh, so basically, we don't have x3. So we can x3 is simple x1, right? So x3 is also 13 by 2. The solution is 13 by 2, 13 by 2, 5 by sorry 5 by 2 and 13 by 2. Okay, this is the solution. Basically, is it sorry x. Is that clear?
Yes, sir. Thank you, sir.
So, what is backward substitution?
Yeah. So this is not the method we are going to use, because this is the substitution method we are already familiar with from the ninth class maybe. But we will use Gaussian elimination, okay, in this course in the upcoming weeks. Any other question?
Sir, AQ 1.2, sir.
Yes, sir. 1.2.
What question number?
Option number 8.
Uh, A is this: use the given condition, find the matrix A for last two options. So, assume A is this: use the given condition to find matrix A for the last two options. First option is there exists some real matrix.
Sir, it is correct only for identity or rather than identity matrix. Option 1.
Okay, so which option you have doubt? Whoever asked this question, which option? I mean, some
All
option are
options,
correct.
sir, all options.
All option you have doubt.
All options, sir.
Let's try one. Okay.
Question number 6, sir.
Question number 8, right? Somebody asked.
Okay.
Okay, so first option we are checking. There exists some real matrix A and B such that AB equals to BA. And what is the condition for this? If AB equals to BA, that means what is clear here?
A is identity matrix, then or B is then it is possible.
Yeah, B is identity matrix, we can say. Okay, because A is already given.
Okay, sir.
I mean, okay, not given. This is just a hint. Forget about this. But AB and BA is possible. In general, it is not true, but for some matrix, it is possible, right? and there do not exist any real matrix A and B such that this is wrong. There does not exist a real matrix A such that A square equals to A. There exists, right?
Yes, sir. 1 1 1 1.
Identity matrix I square is I, or other matrix also there, and there is a special name for such matrix. I think idempotent matrix. Not only identity matrix, idempotent matrix are also A square times I. Okay, there are just some real 2 cross 2 matrix such that okay. So how do we check? How do we check this? We can take this matrix, okay, this matrix as A, and then we can find the
Sir, your voice is not clear, sir.
okay, A11, A12, A21, A22.
Sir, you are not clearly audible, sir.
I'm not audible.
Audible, sir.
You are
Yeah,
audible.
there's lots of background noise.
From my side, not my. Somebody opened his mic. Please
Yeah,
mute.
please mute
Whoever.
Davin.
Sir, that Deepan mic is on.
Okay, so now I should. Yeah, he is muted. Okay, so let's find the A square. Okay, this is A square. So what is A square? A square would be A11 square plus okay, A12 square, right? This is the first entry. Second entry would be A11 A12 plus A 12 A22. Okay, this is
Sir,
second
the
entry.
first entry is A12 into A21, right, sir?
No, this will be multiplied in this column, right?
Yes,
Okay,
sir.
I have this is 2 1, right? So yeah,
Yes.
A11 would be multiplied by A11. This is correct, and this is A12 and A21, right?
Yes, sir.
Yeah, yeah. So basically, this is A square, and similarly, actually we can find these values as well. Okay, then we find the A is already given. We can add, and we can add identity matrix in that. Okay, and then we try to see whether we are getting 0 or not. So uh, we can have actually such matrix. Okay.
Sir, if you will take some real example, if you have, then.
Okay. Not by real example, it is not possible because we don't know which matrix it will satisfy. Let's calculate this.
Sir,
If you want me to solve, let's calculate this. Okay, so a this second entry is correct or not? Second entry, this is correct, right? Okay, let's calculate third one. Third one, this is A21, A11 plus now A21, A12 plus A22 plus A22, and now fourth entry will be is this correct or not? I think I am
No, sir, it is not correct.
yeah.
No, sir. The second
It
entry
should
is wrong.
be
Yeah.
A22 and A21.
A22, A21.
Okay.
Yeah. A21 into A11 plus A22 A21.
Yes, and this one is
Yes.
A2
A21 A12
A12 plus
A22
A22
A22.
yes, A22 is good. So
Yeah.
now plus A. A is A11, A12, A21, and
A21, A22.
and what is identity matrix? 1 0 0 1. Okay, so what when we add these three matrices, what do I get in the first entry? A11 square plus A12, A21 plus A11 plus 1. Okay, and second entry would be second entry would be A11, A12 plus A12, A22 plus A12 plus 0. Okay, so similarly other. So what I do, whether it is 0 or not, we can check this is equals to 0. Okay, so when we make this equals to 0, and again we get some term here also here, when we make all the individual terms equals to 0, uh, and then we can solve. So we'll have four equations, right? Is that clear? We'll
Yes,
have
sir.
four equations, or not four equations exactly. We can actually calculate this and we can verify. Uh, there are some values. We can put some values such that. Uh, so this is just for verification whether there exist or not. We don't have to exactly calculate such metrics. Okay, you have to just say whether such metrics exist or not. So clearly exist, or maybe there is another way.
Actually, sir, I have solved this question like that. We have taken 2 by 2 matrix and square it and add
Yeah, yeah,
and
yeah. See. One more way. So
yeah,
suppose we assume that A is invertible. In
yeah.
that case, we multiply the both side this equation by A inverse. Then we get A plus I plus A inverse equals to 0, right? And in that case, A plus A inverse equals to identity matrix. So this is the equations. So we can take any two such equations so that when we add them to matrices, we can get identity matrix. So this is clearly possible, right?
So what if that means
But A
if
plus A
every
inverse is I, right?
A into
A plus A inverse. Okay.
no A into A
Right,
inverse
right.
are.
A into A inverse is I. Okay, okay, okay.
No, but this is also, I mean, possible. It is just asking exist. This is possible.
Okay.
We can take explicit example if you
Actually, actually, one like in one
yeah,
like in
somebody
one.
wait. Somebody said I have solved this question. Can you tell me your method? I mean, you have
Sir,
assumed matrix, right?
sir, I have assumed like matrix of A is 2 by 2, and then 1, 2, and 2, 3, and square it, then add it, and I is like 1, 0, 0, 1. And I mean, when we uh, multiply and sum all it get I will get 0 result.
Yeah.
Mm,
So basically, that's what we can see here.
yeah,
There are two such matrix. If we add that into it inverse, we can get identity matrix. This is possible.
yes, sir.
Yeah. I mean, there is nothing nothing is stopping us by maintaining this equality. Okay.
So just wanted to ask one thing. So, like basically, in the right hand side, it is asking to compare to a null matrix, right? 0 0 0 0.
Yes. Okay.
Sir, it is
So
We
doubt regarding the third option.
suppose we can do one more thing. Suppose A square equals to A. We already know these matrices are called idempotent matrix, and these matrices exist. In that in that sense, it can also have that A square is equals to minus A. Also possible. In that case, this will become 0, right? And
Yes, sir.
still, okay. There are some
What
other
is
methods.
what is the idempotent matrix? Can you?
Idempotent matrix are following this property: A square equals to A. This is the definition.
Sir, I have a question regarding this idempotent matrix.
Mhm.
So in our course material, there was no mention of idempotent matrix before this activity, right? So how are we going to approach this question, like without prior knowledge to idempotent matrix?
Okay. So
Sir, please complete that option. Last option, it is
Yeah,
correct.
yeah. I will complete that also in this code also, or in this solution. Okay. I'm taking A as A, B, C, D. Okay. I'm checking whether there exists as okay. Let me read the question if there are any other conditions are given. Choose the correct option. A is given. A is a square matrix. Any given? No, no. A is any matrix. Okay. But I'm taking any matrix. Okay, no problem. A is this, and what is the square of this? A, B, C, D. Actually, I've taken this A 1 1 1 2. So this is very confusing. I can take this simple values A, B, C, D, right? So what is this? A square plus BC. Okay, this is the first term, and second term is AB and BD, right? And this is CA plus DC, and this is CB plus D square. Okay, so this is A square. If it is equals to A, B, C, D, okay, this is given to us, and we have to check whether it is possible or not. Okay, there exists such matrix or not. So I'm saying A square plus BC minus A equals to 0. I'm getting. For possible, this condition should satisfy. And from the second term, uh, I can say A, AB plus BD, okay, minus B equals to 0. Is that clear?
Yes,
I
sir.
mean, yeah, we are okay. And similarly, third equation is CA plus DC minus C equals to 0. And fourth one is CB plus D square minus D equals to 0. Okay, so from here, by solving this equation, we can say that there are such metrics exist. Okay, I mean, you can take appropriate values. They are satisfying these values, this conditions, and we can see easily. Okay.
Sir, if I will not get LHS is equal to RHS, then this matrix is not idempotent matrix.
Yeah. I mean, if these conditions are not satisfying, I mean, we are not finding any ABCDs which are satisfying these conditions. That means there are no such matrix. So clearly, there is no violation here. So that's why. So that's why we can be sure that there are such matrix. I mean, dividing by 0, there are no any such condition existing here. Okay.
No, sir. Can you explain one more time?
Okay. Actually, I don't, this is taking too much time, so that's why I don't want to do this explicitly. You can you can eliminate the values one by one. Okay. So this is
Means
A
we
here.
can solve this equation.
Yes.
After that, what we get means end term result. Can you tell me just?
You will get value of ABCDs. I mean,
Okay.
basically, real values of ABCD.
Okay. Then uh,
Not real values.
Sir,
Basically, you will not get any contradiction because it is not asking for matrix. It is just saying there exist or not. So yes, there exist clearly. See, when this condition will satisfy, the matrix exist. It is
Yes,
not
sir.
asking for matrix. That's why it is. That's why.
You can
Yeah.
take a value -1 1 and -1 0. So a square plus a plus identity matrix is equal to 0.
Hmm.
yeah,
Oh, sorry. Can you repeat?
-1 1 and -1 0.
minus.
So
Yeah, this is satisfying. So basically, what I'm saying is, this question is not asking for the solution if that find the such matrix.
It
Otherwise, we
exists.
can sit
Yeah.
and guess. Okay, we can sit. It is just saying whether it there exists or not. So I'm just asking you, is there any problem in this equation?
No, 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 sir.
We can have such value, any value which of a, b, c, which can satisfy this, right? Definitely. Similarly, we can have any values satisfying this. So clearly there is no violation, right? That means there are no such condition, right? Right, denominator is being zero or any other kind of thing, so that we can say this does not exist. Okay.
Excuse me, sir.
Yeah.
Can I have a say? Can you go down to the equation?
Yes.
So from what we found, can we take this minus a to the other side? So our equation will be a square plus bc is equal to a. So our matrix will also be in some kind that the eighth entry should be equal to a square plus bc, and
Yes.
likewise we repeat for b, c, and d. So
Exactly, bro.
yes, yes,
So you got exact. So whenever this condition will be satisfying, uh, the, we will be able to get such matrices. You can see A is this. So whenever this uh, these values are same, and AB plus BD, where is AB plus BD is this. This is equals to B. Okay. Yeah, that's what you are saying, right?
yes, sir, exactly.
Yeah.
So you can do the same for b.
Yeah. AB plus BD, right?
Okay, b is equal to a plus d. You can take the b out, and
Yeah.
okay, yeah,
Out
one
Here we
a,
are.
plus a plus d is equal to 1. So yeah,
plus D equals to 1.
yeah. So we can find a matrix in which satisfies all the condition,
Yeah. Yeah.
unless there is a contradiction.
Yeah. So this is for this condition, right? And now let's take the second one also. The second one, we are getting C equals to CA. Actually, there is no need to solve. That's why I'm actually A plus D.
So in these types of questions, sir, if
No,
we
no.
happen to formulate our expressions and we find out that the condition is valid,
Hmm.
then it is possible for
Yes.
matrix to exist.
Yes. So what I'm saying is, you can find such values A, B, or C, D which are satisfying these conditions. Okay. Suppose A is 1. Okay. A is 1, then D is 0, right? If A is 1, D is 0, which is satisfying this. Now A is 1. Okay. Then 1 equals to 1, and this is B and C, right? Okay. So then we could take this equation here. B and C is also given. Okay. Okay, so this
Actually,
condition is satisfying. Okay, and then A is 1, then B, this condition will get B C equals to 0. Okay, in that case, any of 1 is 0. Okay, so B is suppose 0 and C is 1. So now what matrix we get? A is 1, B is 0, C is 1, and D is 0. But no need to actually do this kind of work. You can see, because we can directly see the solution exists. You can see this. What is the square of this? 1, 0, 1,
0,
0.
1.
Clearly, see, a square equals to. So using this, we are able to find the values, right? We can put any random value. Okay, we are unnecessarily actually taking time.
Yes, sir, I
Uh,
can.
got it? What I'm saying? Actually, no need to find the explicit example. We can directly see. We can have such values clearly. We can take any values as satisfying these conditions. Is that clear or not? So I'm just taking this specific example. If
Yes, sir,
for
clear.
this particular question, if there are such matrices exist such that A square equals to A, yes, exist. Similarly, in the last question here also. So here also we will take A B C D, okay, and then we find such matrix, okay, after this equation. and equate it to 0 because here. And similarly, we can randomly choose values of A, B, C, D such that those conditions should be satisfied. Okay. Any doubt in this?
No, sir.
Okay. Anyone, if you have any doubt, you can ask.
Sir,
Question
please
number 6.
explain the question 6, sir.
6. Assume that again these metrics are given. First
So,
option, if A is a square matrix of order 2 and A square equals to I, then A is I or A is minus I, where I is identity matrix of order 2.
So in previous question, last option,
Hmm.
if matrix is 3 into 3,
Hmm.
same thing will happen. No?
Yes. I mean, this is the beauty of this. If it is true for 2 by 2, then it is true for any matrix. Okay.
Oh, okay, sir. Thank
Yeah.
you, sir.
Sir,
Okay. Yeah. So question number 6 we are discussing. Question number option number 1. Let me take the screenshot of this. Okay. So what is the first option?
A square or I into
A is I and A is minus I. So is it possible? Definitely, right?
yes.
Because uh, if A is, oh, it is saying A is I minus I.
how minus I, sir?
Suppose A is minus I
Yeah,
and we are multiplying by minus I. Okay, because we have to just check this condition. Is it
okay.
coming? I, yes.
Yes.
In both case it is satisfying.
Uh, sir, but in the check answer option, it is showing that this option is not correct.
Yes, yes, sir. There's the like actual
This option
issue.
is incorrect.
Yes, sir.
That's what the check answer of function is
Okay.
saying.
If A is a square matrix of order 2 and A square equals to I, then A is this or this. Oh, it is actually restricting this. I mean, it is saying if
Maybe
A
there
square
can more matrices.
then
Yeah.
only this is the case. I thought it is the case. So this is true, but this is true for others also. Okay. When it is true, we can take explicit example. Okay. So again, same condition actually A, B, C, D. That's actually we don't have any other option, any other choice. You have to take these two and multiply and actually calculate those equations and then randomly choose the values of A, B, C, D. Okay. I if I can solve for this option if you want. Okay, what was the multiplication? Actually, I don't remember. What was the multiplication? Somebody tell.
Yeah, A
A,
square plus BC,
A square plus BC
AB plus B plus BD,
plus BD
AC
AC,
plus BC, CD, CD, sorry, yeah. Sir,
yeah,
CD.
CD. Okay,
Yeah, yeah, CD. And
and
BC plus D square.
BC plus D square. Okay, so this is A square, right? So what we can do? We can take A square in the first entry, and this is equals to 1. And second entry, AD plus BD equals to 0. And this AC plus CD equals to 0 again, right? And BC plus D square equals to 1.
Yes, sir.
Okay, uh, uh, we can solve this equation. Okay, so what we are getting, A uh, D equals to minus BD. Okay, so D we can cancel. So A equals to minus B.
Minus B.
And from here also I think we are getting, oh, here we are getting A equals to minus D, right?
Yes.
From this equation.
Yes,
Yes,
sir.
sir. Yes, sir.
There are two conditions we are having. So suppose A is 1, then D is A is
Minus.
-1.
A is 1, then D is minus. We get two values. Now put here A is 1, uh, then BC equals to, okay, not put in this, put somewhere else, okay, because again we are getting BC equals to 0, 0. But okay, no problem. That is not our problem. Uh, we have A is 1. Okay, so take some other value. Suppose A is 2, because
We have to solve for one more, sir. As we solve for A, then we have to solve for one more.
yes, yes. Actually, this option, this example also work. A is 1, but I'm just want to take different option, just for no reason. Okay, so 2 and minus 2. So now A is 2, so A square is 4. Okay, okay. This is the first condition, right? So I'm writing here. A square is 4, so B square BC is minus 3. Okay, is that correct? Now we can take such value. Suppose B is 1 now, then what is C?
Minus 3.
Minus 3. Okay, so we have B, C, and AD. So what is the matrix I get? 2, minus 2, and 1, and minus 3. So we found this matrix. So basically what I'm saying, we don't have to do these activities. We can directly see, yeah, we can find such values. Okay.
We can do one more thing also, like
No,
if
no, sir. Why we change the example for 1 to 2 basically
And for
while
no
taking the
reason,
value for A is equal to
for,
2? Yeah.
because what will happen, so that matrix we are getting, suppose 1 minus 1, and because this is 1, so bc equals to 0, bc equals to 0, so any one of them is 0. Suppose b is 0,
we
and then and c is suppose 1. Okay, so b is 0 and
so
c is 1. Yeah, so this is also satisfying this a square equals to I.
yeah, we can do one thing also, like say for example, in this case we have taken B as well as C equal to 1 and D equal to 0. So
Hmm.
probably, if we work like that, then also we get 0, 1, 1, 0, which
Yes.
is not a identity matrix. So we can
Yeah.
solve in that manner also. Yeah.
Yes, yes.
Sir, actually, while solving the equation,
Exactly.
you see that A
Yeah,
equal
for
to
this
minus B and A equal to
actually
minus D, sir. I did not get this point actually. Why this is A equal to minus B and A equal to minus D? Yeah, this one.
this one, this is coming from this equation, this equation. Okay, and where this equation is coming from here, we have multiplied this, we have found a
Yeah,
square.
yeah, from the general equation. Yeah.
Okay, we are equating that to identity matrix. So for identity, these two terms are 0 and these two terms are 1. Okay, got it or not?
Okay, sir. So what we conclude here actually, I did not get.
Hmm. We conclude that it is saying uh, that only a is minus I and minus I. In that case, this is true, which is not the case. This is also satisfying. This is also satisfying. And somebody tell one more example. There are many matrices, not necessarily I or minus I. Okay,
Sir, can you explain why
Okay.
option 1 is incorrect?
or yeah, that's why option is incorrect, because there are other matrices also possible
Got
other
it.
than I and minus I. And one more way to solve this is easy method is we can actually multiply both side by A inverse. Suppose in that case, the A would be A inverse. Okay, so A is A inverse. In that case, Hmm. Oh, okay, but that in that case is must be invertible, right? It is not given here in this question. We cannot assume that A is invertible. Okay, so first option is wrong. You understood why? It is
Sir, while solving that those equations, I think the second equation that you made is incorrect, sir. That is AD plus BD is equal to 0. Uh, it should be
A equals to minus B, right? So it is correct.
It's correct, I think. Yeah.
AD plus BD is equal to 0. You have written.
It's AB plus BD.
It is A AB plus BD. It is not AD. It is B. Yes.
Okay, AB. In that case, yeah, A. In that case, we have must got this option also wrong. Okay, so that means these are also wrong examples because we are assuming that A equal to minus B, but here should be A equals to minus. Okay, this is the property, and rest of the property will according to that.
Yes, yes, yes. Yeah, actually, that's was the my confusion. Like basically, in the same equation, how it can be equal to two things basically, equal to minus D and equal to minus B.
So
I
I
got it, sir.
miscalculated that. Okay, that's why this confusion.
Got it, sir. Yeah, it's
Sir,
clearly.
Hmm.
for that same equation where you have written A square is equal to I, sir,
Hmm.
if we multiply both the side by A inverse like you did earlier,
Hmm.
then we are going to get A is equal to A inverse,
Hmm.
and then we take determinant on both the sides.
Yes.
That means determinant of A is equal to determinant of A inverse.
Hmm.
And we already know that determinant of A is 1 by determinant of A inverse.
Yes.
And now we solve this equation by assuming determinant of A is equal to x. Then
Hmm.
we are going to get an equation x square minus 1 equal to 0. So by this way, we are always getting x as plus or minus 1.
Yeah. Determinant. We are getting plus one minus one. So
Yeah,
all those matrices who
where
have
the determinant is plus minus 1 will be applicable over here.
will be satisfying this condition. Yeah.
Okay, sir. Yes, sir.
Okay. So yeah, there are a lot of explanation for this question. Okay, that's why this option is wrong. There are all those matrices which have determinant one or plus one or minus one will be satisfying this. Okay, got it. Yeah, so we
Yes,
no
sir.
need.
Actually, there are so many equations, like so many matrices, so that's why it's incorrect, right, sir?
Yeah, so first option I'm just resolving uh, using this method. Okay, there are so many matrices. Whenever the determinant of that matrix is one or minus one, it will satisfy. So why it is assumed? This I and minus I, because these matrices also are determinant one or minus one, but there are other matrices also. So whenever a matrix has determinant one or minus one, it will satisfy this. Okay. So second option is if A is a square matrix of order 2, A square equals to 0, 0, then A is 0. So again, we can actually do the same thing. We can take the determinant both sides. Okay, this is 0, and this is the determinant of A square equals to 0. So determinant of A times determinant of A equals to 0. Okay, we can write this. What it is saying, A is a square matrix of order 2, A square equals to 0, then A is also 0. Hmm. Hmm.
It would be incorrect, right? This is not true for every A.
Yeah, so for this we have to actually come to this method, and now we will make this 0. Okay, and then check there are other matrices also. Okay. Okay, so one more thing we can do, uh, again multiplying by A inverse both sides. So we'll have A equals to 0. Okay, so I'm multiplying A inverse, then it is coming A is equal to 0. But there should be other matrices also. Okay, so for that we have to solve from here also, here as well. Okay, so for that, first is A square plus BC equals to 0. Okay, and second equation is AB plus BD equals to 0, and similarly other options, other equations. So we will solve for this one. What it is coming again, B will cancel out, A equals to minus D. Okay, so whenever this condition will satisfy, we can get other matrices as well. Okay, and from here, because A is minus D, so basically there are other matrices clearly, right? Are you getting my point, what I'm saying? I mean, A is suppose A is 1, okay, and D is minus 1, and these are 0. Okay, so what will happen now? 1 0 0 1, minus 1. Can you calculate this? What will come? 0. Okay, we are not getting 0 here. We need one more equation. Okay, but this is the one condition, and one more condition we need. Maybe from here. PC plus D square is 0. Okay, we can actually subtract these two equations. So we get A square minus D square is equals to 0. So A square equals to D square. Okay. Or A plus D equals to 0 and A equals to D. So these are the two conditions we are getting. We are trying to find a counter example basically. Okay, and from here, can somebody suggest me any counter example for this?
If A plus D is 0, then how is
Sorry, are you asking something?
Yeah, I'm asking if anybody has the counter example for this.
So can we use another approach, sir? Can I suggest something, sir?
Yes.
Sir, as the question says that if A square is given as 0, and we want to check whether A is equal to 0 or not. So let's assume A square is equal to 0 and A is also 0. So it means that A square is equal to A. We are just assuming it for the time being. So we can write A square is equal to A.
If you want a matrix, then it would be 0 1 and 0 0.
Then we solve this equation.
Yes,
We get two
0
values.
0 0.
There can also be matrix 1 minus 1 1 minus 1. That is also one.
Yeah. 1 minus 1.
1
Sorry.
minus 1. Yeah.
1 minus 1 and
1 minus 1.
1 minus 1. Yeah, so this is the counter example for this. Okay, so this is also satisfying. Whenever we square this matrix, we'll get 0, right?
Yeah.
Yeah, so it is not necessary that A must be 0.
Yes.
Okay. Okay, so rest of the questions we'll discuss tomorrow. Okay, it is a 2.5 hour. Okay, tomorrow is also such session. Okay, no problem. All the problems, all of your doubt will be discussed there. Okay.
Thank you.
And sir, I also see some question in graded assignment and PA as well. Like they are solving with row reduction or something like that. But we did not introduce in first week row reduction something like that. So how can we say?
Row reduction. No, row reduction is in week 2, right?
Sorry.
Row reduction is in week 2.
Yeah, week two. But we getting question in week one itself
Yeah,
in
we'll
some
see.
PA and GS also.
We'll see it tomorrow. Okay, no problem.
Okay, okay, sure, sir.
Let's take a break to tomorrow. So tomorrow session is from 8 to 10. So we'll discuss all these doubts as well, and this what is your doubt? Okay.
Okay, so you are going to take the session for the tomorrow session as well, right?
Yes, yes.
Yeah. Okay, okay, sure, sure. So there are how many TA session per week? Yeah, per week basically.
There are 2 TA session in a week. Okay.
Okay, sir.
And
Okay,
two
thank
and
you.
two instructor session, right?
Yes. Okay. All of you, thank you.
Yeah,
Completed.
sure. Thank you, sir. Thank you so much for the explaining the
Thank you, sir.
concept.
Thank you, sir.
Thank you.
Thank you.